Today we're going to talk about the Shapley-Shubik Power Index. The Shapley-Shubik Power Index is just another name for the Shapley value when we're applying it to certain decision-making systems such as voting. Here's the definition, an important definition in this area. We call a game, this is a game in coalitional form, N is the set of players, V is the characteristic function. We call a game simple if for every coalition, the value of that coalition is either 0 or 1. A coalition which has value 0 is called a losing coalition. A coalition with value 1 is called a winning coalition. It's easy to see that because of superadditivity for the characteristic function, anytime you have a subset of a losing coalition, that's still a losing coalition. Anytime you have a superset, a set that contains this coalition, of the coalition S, that will also be a winning coalition. Here's some basic examples of games in coalitional form that involve voting. A standard one is majority rule. You have N players. We say the value of a coalition is 1 if the size of the coalition is greater than 1/2 N. That means it's a majority. And we say the value of the coalition is 0 otherwise. Now, what's the Shapley value for this characteristic function, or in other words, the Shapley-Shubik power index here? We can answer that immediately without any detailed computations because this game is entirely symmetric in all the players. So since there are N players, we can say that phi sub I of V will be exactly 1 over N for each I equals 1, 2, up to N. Here's a different sort of voting system. It takes a unanimous vote for something to pass. In such a system, the value for the grand coalition is 1, but the value for every other coalition is 0. Well, this is a very different sort of voting system. Many fewer ideas or choices will be approved, only if there's a unanimous consent. But again, everybody is treated similarly. If there are N players, each one has a value of 1 over N. These are both by symmetry, by the symmetry axiom for the Shapley value. Now here's a more exciting sort of voting system. You have one player, we'll call it player 1 out of the N players, who gets to decide every issue that comes forward. We say the value of a coalition is 1 if player 1 is in the coalition. Player 1 gets the name of dictator. The value of a coalition is 0 if it doesn't include player 1. If it's everybody other than player 1, it still has value 0. Basically, everything player 1 wants, player 1 gets. Well, what can we say about the Shapley value in this situation? Well, the dummy axiom tells us that the value for any player other than the dictator, player 1, must be 0 because they cannot ever change the value of a coalition from 0 to 1 by their addition. And so this will be true for all I equals 2, 3, up to N. And of course, since the total has to be 1, the value of the grand coalition is 1, it's easy to see that phi sub 1 of V is exactly 1. Another way to see that phi sub 1 of V is 1 is you just average over any ordering of the set of N players, average the contribution of adding player 1 to the coalition of the players that came before. Well, every single time the coalition of players that came before player 1 had value 0, you put player 1 in there, you get a value 1. So every single time in all N factorial ways to order the grand coalition, player 1 adds a value of 1, so the average is 1. So the dictator gets the value 1, everybody else has a value 0. Now, for any simple game, the value of any coalition is either 0 or 1. So if we're going to use this method for computing the Shapley value of looking at all the n factorial ways to order the grand coalition and asking, say, for player I, how much extra value is added by including player I, that extra value, the value of S minus the value of S minus I, this is for a coalition S that includes player I, this is the value added by increasing the coalition of S minus I by putting player I in it. That difference is either 1 if there was a losing coalition without player I and the winning coalition now with player I, or it's 0. It's 0 if you already had a winning coalition going in, or if you had a losing coalition and you still have a losing coalition after player I is added. So this quantity is either 1 or 0. If we want to use our formula for the Shapley-Shubik power index, phi of v, phi1 of v, phi2 of v up to phi n of v, for this payoff vector, this payoff vector, now remember, we're interpreting as a power index, telling you the power of each of the n players. We can find the formula for phi sub I of v by multiplying this quantity. Well, 1 over n factorial comes from averaging over the n factorial different orders. The size of S, if S is a winning coalition where S minus the set I is a losing coalition, the size of S minus 1 factorial is the number of ways to order that losing coalition, S minus the set I, order those players that came before player I. Then we add player I, and we're multiplying this quantity by, here, v of S minus v of S minus I. Of course, this will just be equal to 1, so that's why we didn't even write it there, because multiplying by 1 doesn't change the formula. So if we had a losing coalition without I and a winning coalition with I, we have this many ways to order the players that came before I, n minus the size of S factorial ways to order the players that came after I, and we're multiplying each by that added value, which is exactly 1, which of course we can erase because multiplying by 1, as we already said, doesn't change anything. And we're adding those all up, each over n factorial, because we're averaging over the n factorial orderings of the grand coalition. So it tends to be easy to compute this Shapley-Shubik power index with a formula like this if we can understand exactly which coalitions are the ones, say for player I, which we're losing without player I, but which player I turns into, the addition of player I turns into a winning coalition. Let's see a few examples. Oh, in just a minute. Let's start with one more definition and then we'll see some examples. Here, we want to define what we mean by a weighted voting system. If each player has a weight, W sub I, we normally demand that this be a non-negative number. It could be 0 if you want to give a player a 0 weight, but normally it's either 0 or a positive number. Each player, I equals 1 through n, gets a weight, and we have some number q, which is the quota, like the threshold, which must be reached in order to declare a winning coalition. Then we want to say the value of S of a coalition is 1 exactly when the sum of the weights of the members in the coalition is greater than that threshold Q. Here's an example, and common examples might involve a system where you have people who own stock ownership in a company. Each stockholder has maybe a different number of shares of stock. The weight W sub I might represent the number of shares for player I. Here we'll do a simple example where we have only 4 people who own shares in a company. All the shares in the company are owned by these 4 people. And the 4 shareholders, let's call them players 1, 2, 3, and 4, own 40, 40, 40, and 30 shares, respectively. So there are 150 total shares in this company. When important corporate decisions come up and it goes to a shareholder vote, the measure passes if the total number of shares constitutes a majority. It has to be greater than, can't be equal to, but it has to be greater than 75 shares. Now, what is the relative power for these 4 shareholders? Well, it should be pretty clear that the 3 shareholders, 1, 2, and 3, who own the exact same amount of stock, have an equal power in the company. But how much power does the fourth shareholder have? Let's ask ourselves, what are the winning coalitions here? The winning coalitions are those that combine to have greater than 75 shares. That could be player 1 and 2, it could be player 1 and 3, it could be player 2 and 3. It could be any superset of those, which means it could be 1 and 2 and throw in player 4 as well, or it could be 1, 2, and 3. But the simplest winning ones must include one of the following. Must include either player 1 and player 2, or player 1 and player 3, or player 2 and player 3. Player 4, along with one of these others, can't form a winning coalition. Player 4 with two of the others can form a winning coalition, but it would still be a winning coalition without player 4. In other words, it's easy to see that there is no losing coalition that doesn't include player 4, which becomes a winning coalition when you include player 4. The only losing coalitions among these other players would be just one of them with 40 votes. Adding player 4 never turns that into a winning coalition. So what does that tell us about player 4? Player 4 meets the conditions of the dummy axiom, doesn't add any value to any coalition that's already formed among the others. Well, if the player 4 doesn't add any value, then we know that V4 of V must be 0. And by symmetry for the other three players, we have V1 equals V2 equals V3 equals 1/3. So even though they all hold shares of stock, player 4 holds almost as much as the other players. Player 4 has no say in anything in this sort of voting system. Another example. Let's say we have a family with two parents. I'm going to call the parents A and B, and 5 children. Now, it's the policy in this family, the parents probably made the policy, that if an important family decision must be made, it can be made with the support of either both parents, regardless of what the children think. Let's say the 5 children are C, D, E, F, and G. Or it could be, the decision can be made by having one parent along with the majority of the children. 3 children going along with one parent can make a decision. For example, let's say they want to go to a movie and choose the movie. The choice will be made if both parents agree on the movie and they just take the kids to the movie they want to. Or one parent and a majority of kids can make that decision just with that coalition. What are the relative powers of the different players in this game? In this case, the parents and the children. Right away, we can see that the 2 parents are in a symmetric situation. So phi sub A will equal phi sub B. And the 5 children are all in a symmetric situation with each other. So phi C equals phi D equals phi E equals phi F equals phi G. How will we compute all of these different values? Well, if we can compute any one of these, then knowing that all of these are equal, and knowing that these 2 are equal, and that the sum of all of them is exactly equal to 1, we can find all of the others. So we really need to compute just one. How will we compute, for example, phi sub C, which is the Shapley value for one of the children, say child C? Well, we have to ask ourselves which coalitions that are losing coalitions become winning coalitions when we add this one child. And it's pretty easy to see the only way a coalition could be a losing coalition that turns into a winning coalition by adding child C is if the original coalition had, just 3 players that consisted of 1 parent and 2 children. Then when you added in child C, you would have 1 parent and 3 children. That would form a winning coalition. And then, of course, later you would have the other 2 children and the other parent. So our question is to count, of all the 7 factorial, which is 5,040, different ways to order the Grand Coalition, how many of them have child C right here in the middle, where the first three consist of one of the parents and two children, and these last three consist of another parent and the two other children? Well, we can count such situations by first asking which parent it is. Well, it could be parent A or parent B among the first three in the coalition that comes before child C. There are two ways to choose that, A or B. Let's just put as an example parent A there, but there are two different ways it could go. Now, we also have to pick two of the other children. There are four other children D, E, F, G. I claim there are 6 ways to pick two of these other children. From the 4 children, D, E, F, G, how many ways can we pick 2? It could be D and E, it could be E and F, it could be F and G, it could be D and F, it could be E and G, or it could be D and G. In combinatorics, many of you will probably recognize this is just the number 4, choose 2. But you can just easily list all of them as I just did and see there are 6 ways to pick which children. So to pick which children, I'll just put an example here. It could be D and F. 6 ways to choose which children. Now these 3 people, D, A, and F, could be arranged in 6 different orders for these first 3 people. That's 3 factorial. 6 orders. Finally, once you've chosen which people go here, you know exactly which people go on the other side. It has to be parent B, it has to be child E, and child G. But again, there are 6 orders possible for rearranging those children. So in order to pick a coalition that goes first 3 people, 1 parent and 2 children that don't include child C, then child C, then the other parent and the other 2 children, the total number of ways this can happen is 2 for which parent, times 6 for which of the other children that go before C, times 6, which is the number of orderings, times 6, which is the number of orderings for the last 3 people. And one can easily compute this number, 2 times 6 times 6 times 6, but I won't even bother right now, because what we know about phi sub C is that we count the number of orderings that make C the linchpin, in other words, the one who turns a losing coalition into a winning coalition. There are this many such orderings, and we divide by 7, in this case 7 factorial, the total number of orderings for the grand coalition. We can compute this just by taking this number, 2 times 6 times 6 times 6, and dividing by 7 factorial, which is 2 times 3 times 4 times 5 times 6 times 7, and we just cancel things. The 2 cancels the 2, the 6 cancels the 6. Let's see, this 6 can be canceled by the 3 and the 4 with the 2 remaining, and the 6 divided by the 2 makes it a 3. This ends up being 3 over 5 times 7, which is 3 over 35. So what does that tell us? It tells us that each of these is 3/35. And when you have 5 numbers which are each 3/35, that totals 15/35. So we have remaining 20/35 to divide among these 2. So these are each 10/35. Now you can do a similar computation, and I've done this. It's a bit messier than what we just did, but it's a good exercise for all of you to show individually that a single parent, like parent A, gets a Shapley value of exactly 10/35. So the Shapley function will be exactly this. Phi will be this power index that gives 10/35 to each parent and 3/35 to each kid. So you'll see that the way this voting system is set up, the parents, each individual parent is worth more than 3 kids in this voting.